Welcome back to this short series on the fundamentals of control engineering. In the previous video, we have seen that linear systems are a special case of a more general class of dynamical systems, which has a few interesting properties. In particular, we have an explicit representation for such systems, and we can classify them based on the stability of the natural modes associated to the dynamical matrix of these systems. So why are we so interested in linear systems? Well, there are two main reasons. The first one, as Richard Feynman famously put it, is that we can solve linear systems. And the second reason is that we can use linear systems to approximate the behavior of nonlinear systems in the vicinity of equilibrium points. Well, let's see now what are equilibrium points. So these are points where the derivative of x is 0, which means that the state will stay in such points indefinitely. And typically when we speak about equilibrium systems, we are specifically interested in equilibrium systems in which the input is 0, so under no external force. In the case of linear systems, we have that f is just the product of the matrix A times x. So if A is full rank, our equilibrium equation, which is A times x equals 0, will just give the solution x equals 0. When A is not full rank, we might have slightly more complicated cases, but we won't consider them for now. Moreover, equilibrium points might have different properties. So let's make a couple examples. First of all, let's imagine we have a pit and we'll let a ball roll into it. So this is clearly an equilibrium point because the ball will stay there if nothing happens. Moreover, if we slightly displace the ball, then it will just roll back into this valley and go back to its original position. On the contrary, if we have a situation like this, where we have a hill on which we balance a ball, then this is also an equilibrium point, because if no force acts on the ball, it will just stay balanced on the hill. But if we give a gentle nudge to the ball, it will roll away and get far from the equilibrium point. Another famous example is that of a pendulum. So imagine you have a hinge and a mass attached to it and free to oscillate. Then the downward position is an equilibrium position because the pendulum will just stay there indefinitely if no force is applied to it. Moreover, if we displace it from the equilibrium point, it will just swing back into its original position. On the contrary, if the pendulum is upwards, then even a small displacement will make it go away from the equilibrium point. For equilibrium points of linear systems, we have seen that we can use the Hurwitz criterion. And in particular, we have said that an equilibrium point, which will be the origin in our case, as we have just seen, for a linear system in the form x dot equals A times x. So the origin will be asymptotically stable if and only if all eigenvalues of A have negative real part, marginally stable if there's one and one only eigenvalue with zero real part, and unstable otherwise, which means whether we have positive real part eigenvalues or more than one zero real part eigenvalues. Now, the reason why all of this is interesting is that we can use the process known as linearization to approximate the behavior of nonlinear systems close to equilibrium point. So let us consider the system x dot equals f of x and u. And let's assume that x star is an equilibrium point such that f of x star 0 is 0. Now we can approximate the behavior of the system close to x star by using the Taylor series of f. So we write x as x star plus a small displacement dx. And now we can apply f, so this will be x dot actually. And let's assume we also have a small control action u around 0. Now, At first order, this will be equal to f of x star 0 plus the derivative of f with respect to x computed in x star 0 times delta x plus the derivative of f with respect to u in the same point times du. And now we observe that the derivative of x star is 0 and that f at the equilibrium point is also 0. What we are left with is the system delta x dot equals df over dx at the equilibrium point times delta x plus df over du at the equilibrium point times delta u. And this is just a linear system. Moreover, we have a very interesting result, which is the Hartmann-Grobman theorem, which we won't state in a formally correct way, but we'll just give the general idea, which states the following. Imagine we have an f function that takes values in Rn and is applied on a variable in Rn. And this f is moot. Moreover, assume that we have an equilibrium point x such that f in this function is 0. For now, we are considering the case with no external inputs. And let's assume that the derivative of f with respect to x in this equilibrium point has no zero real part eigenvalue. Then the linearization is a good approximation close to the equilibrium point, which means that we can study the stability of the equilibrium point with the Hurwitz criterion. Let's make an example. Let us consider a pendulum. So again, we have a hinge, the vertical axis, and a pendulum. We neglect the mass of the link, so we only consider the mass m of the pendulum, the length of the arm, and the angle theta. And the equation for the system are the following. We have m L squared theta double dot equals minus mgl times the sine of theta minus bl theta dot. And note that these equations are very similar to the equations of the damped harmonic oscillator we have seen in the previous video. So we can write this as theta double dot is minus g over L the sine of theta minus b over ml theta dot. And as we have done in the case of the damped harmonic oscillator, we will introduce an additional state variable. So the system will become theta dot equals omega, and omega dot is minus g over L the sine of theta minus b over ml omega itself. Now the equilibrium points for the system require that omega is 0, of course, and that theta, once this term disappears, is equal to a multiple of pi with k, an integer number. Now we can distinguish between two different situations. The first one is when the pendulum is downwards. This means that omega is 0 and theta is either 0 or a multiple of 2 pi. So it's 2k pi. In this case, as we said, we expect to find a stable equilibrium. While the opposite case is when we have the upwards pendulum, which means that omega equals 0 and theta is an odd multiple of pi. Now, let's see whether we can notice anything about the stability of these points by using the Hartmann-Grobman theorem. So the Jacobian matrix is the following. df over dx is 0 minus g over L cosine of theta, 1 minus b over ml. And in the first case, this becomes 0, 1 minus g over L and minus b over ml. You may recognize that this is exactly the same system that we had in the case of the damped harmonic oscillator. So we'll have two stable decaying oscillating modes. And in fact, the eigenvalues for this system are given by the following expression. Lambda is equal to minus b over 2ml plus or minus 1/2 of b squared over m squared L squared minus 4g over L. And if 4g is smaller than b squared over m squared L, then the term under the square root is real, and we will have a damped motion. Well, if 4g over L is larger than b squared over m squared L squared, which is the case for a small damping factor b, then we'll have oscillating modes. In the other case, our Jacobian becomes 0, 1 plus g over L and minus b over ml. And you immediately see that the only term that changes sign here is the minus 4g over L term under the square root, which means that in this case, one of the roots will always be positive. Let me write this down in full. So in this case, we have lambda equals minus b over 2 ml plus or minus 1/2 of b squared over m squared L squared plus 4g over L. And in particular, you see that whenever we choose the plus sign here, then the term under the square root is larger than b over 2 ml, and the whole sum here is positive. So we have an unstable equilibrium point.